The second topic that we have for today is entropy. And much is said about entropy. A simple way of describing entropy is that it's a measure of disorder or the idea to how much something is disordered. Now, entropy is natural. So, for example, आपका कमरा है, एक दिन सफाई करते हो आप अपने कमरे की, everything is set, everything is clean, सब कुछ है. And any reasonable person will not deliberately mess their room up, right? वो खुद से आप उसमें उसको खराब नहीं करोगे. बट आफ्टर अ वीक अगर आप उसकी कमरे की लेट सपोज उस पूरे वीक में आप सफाई नहीं करते हैं, इट विल लुक लाइक अ मेस, इट विल बी अ मेस. Nobody deliberately did that, but it's just the natural order of things. The disorder will be there, and the signs of disorder will be there. Now, everyday life is like that. Disorder is going to be there, and it's always going to be increasing. And that's, in science, we call it a second law of thermodynamics. Another important thing is the idea of spontaneity. And spontaneity goes hand in hand with entropy. Spontaneity, वैसे तो हम loves का मतलब ये लेते हैं कि somebody who's doing things right in the moment and all. But spontaneity in the terms of chemistry, we're going to assume things that can easily go from a state of high energy to a state of lower energy. For example, exothermic processes, given the activation energy, they're very quick to happen. And many processes that are exothermic happen more easily in nature than processes that are endothermic, because in endothermic, you have to move them to a high energy state. A book can fall from a shelf down to the ground, but वो खुद ही से उठ के नीचे से ऊपर नहीं जाएगी, because that's not going to happen spontaneously. But it can fall to a lower level because अगर वो कहीं पे है और वो टूट गया वो it's going to fall down. That is just the idea of, number one, energy changes. Obviously, it's going to lose the gravitational potential energy it has accumulated because of that position. But also that this can happen spontaneously. It doesn't have to wait for something else to happen. The moment it's given a chance, it's going to do that. So a crystal, for example, of sodium chloride or anything else, there's a lot of order there. But the moment it gets a chance of, let's say you add it to water, it's going to break down, it's going to go around in a disordered, random arrangement of ions moving around. ठीक है. और ये जो डिसऑर्डर होगा ना, इसको हम एंट्रोपी कहते हैं. और एंट्रोपी को हम साइन भी दे सकते हैं, एंट्रोपी की वैल्यू भी होती है. और एंट्रोपी का सिंबल होता है एस, एंड इट हैज यूनिट्स ऑफ जूल्स पर केल्विन पर मोल. So that might give you some idea of what energy is. It is the energy change per unit temperature per mole. So kind of like saying कि अगर आप एक डिग्री, एक मोल किसी भी चीज का लो और आप उसको सिर्फ 1 डिग्री टेम्परेचर ज्यादा दो, तो काइंड ऑफ लाइक यू हैव गिवन इट मोर एनर्जी, राइट? हाउ मच दैट एनर्जी अफेक्ट्स द डिसऑर्डर ऑफ थिंग्स. अगर लेट्स सपोज यू हैव टू थिंग्स, वन इज हाइड्रोजन गैस, वन इज सोडियम क्लोराइड. हाइड्रोजन गैस की एंट्रोपी इज ओवर 100 at room temperature and pressure, and sodium chloride is less than 100. What does that tell us? It tells us that for hydrogen gas, if you give it just 1 degree temperature uska rise karoge na agar aap, so the way the particles are going to be disordered, the way the particles are going to move around randomly, it's going to be much more than the way sodium chloride particles will move if you change the temperature just by 1 degree Celsius. So 25 से 26 पे जाने में कितनी उसको disorder create होता है, उसको हम entropy कहते हैं for 1 mole. So obviously उसको multiply कर सकते हो आप based on different temperature and different moles. You have used something like this before as well. Remember Q is equal to mc delta T temperature. उसमें the C was specific heat capacity. The heat capacity was a measure of कि अगर आपने 1 किलोग्राम को 1 डिग्री सेल्सियस टेम्परेचर इंक्रीज किया तो उसको लिए आपको कितनी एनर्जी चाहिए. सो दैट वाज हीट कैपेसिटी कि 1 किलोग्राम का सिर्फ 1 डिग्री सेल्सियस टेम्परेचर बढ़ाना है. एंट्रोपी इज कि आपने 1 मोल का 1 डिग्री सेल्सियस टेम्परेचर बढ़ाना है, उसके लिए जो एनर्जी आप दे रहे हो उसको, दैट इज एंट्रोपी. सो यहां पे आप मोल्स में कर रहे हो, वहां पे आप किलोग्राम्स में कर रहे हो, बट द अंडरलाइंग आइडिया इज स्टिल द सेम. एंड वहां पे हम किलोग्राम में क्यों कर रहे थे? बिकॉज वी आर सेइंग कि मास को हीट अप कर रहे हैं. यहाँ पे वी आर नॉट लुकिंग एट मास इन जनरल, वी आर लुकिंग एट पार्टिकल्स, क्योंकि मास तो हाइड्रोजन और सोडियम क्लोराइड का सेम हो सकता है, but the particles that are in there will not be the same if the mass is same. So the particles, the way those particles are going to be moving around, or the way their energy is going to be increased, that is the measure of entropy. Does that make sense? All right. Now, obviously, judging by the states, we can say कि इसकी entropy ज़्यादा है, इसकी कम है. Water as a liquid will have lower entropy than gas, the water vapor that you have. So if you write that H2O liquid and it changes to H2O gas, not only do you have to supply energy to change the state and overcome the forces, but while it is in that state, the disorder is going to be much, much higher than the disorder was in the liquid, even though we say both of them are random. So the delta S with this circle for the standard thing for this case is 119 joules per Kelvin per mole. So this is telling me कि 1 डिग्री का भी अगर हम इंक्रीज करते हैं इसका, तो इतना ज़्यादा इसकी एनर्जी में फ़र्क पड़ेगा. In some process, this can be negative. In some process, this can be positive. So for example, अगर मैं इसका reverse करता हूँ, तो it's going to be negative. Same value, but it will be negative. You can also figure it out in के जैसे हमने एक diffusion का reaction किया था, the very first reaction that students in O levels usually see, कि this makes ammonium chloride, right? And white solid appear होता है. This is a solid, that's a gas. You have two gases coming together to make a solid. There's going to be a drastic drop in the entropy because पहले वो fully randomly move करते हैं, and now they are confined to a solid state, a lattice. So there's going to be a decrease in the value of entropy. So positive and negative simply tells us the way it changes. Uh, obviously, many factors affect it. State does, but more than that, the kind of bonding that it has. मतलब दोनों solids हैं, लेकिन एक में bonding बहुत strong है, तो उसका change in entropy will be much less, क्योंकि वो उसको इतना ज़्यादा effect नहीं करता. Okay? So for example, diamond को अगर आप 1 डिग्री हीट करो और सोडियम क्लोराइड को 1 डिग्री हीट करो, the entropy in sodium chloride is going to be much more comparatively. क्यों? क्योंकि डायमंड में particles की force of attraction बहुत ज़्यादा है, and they're going to be really, really close to each other. Okay? So that's the idea. So just to understand whether you know and you understand this, tell me whether entropy rises or falls in this reaction.
Decreases.
Why?
Gas moles are decreasing.
Good. How about now?
Increasing.
Good. How about now?
Stays the same.
Yeah, you can say that they stay the same, but of course, we are not sure if they do. We'll have to obviously look at the values. By the way, fluorine and chlorine are both gases. Which one do you think will have a higher standard entropy?
Fluorine.
Kyun?
Smaller atom to like ज़्यादा disorder, I guess.
What do you mean smaller atom?
Mass छोटा था इसलिए.
What does that have to do with the way the particles are closer together and they are not allowed to move around more? What does that have to do with it?
Heavier atom, I guess, moves less.
Moves less? मतलब आपने उनको एनर्जी देनी है और वो डिसऑर्डर कितना ज्यादा उनमें क्रिएट होएगा. They're both gases, right?
Yeah.
तो क्लोरीन के अंदर फोर्स ऑफ अट्रैक्शन और फ्लोरीन के अंदर फोर्सेस ऑफ अट्रैक्शन प्ले अ रोल इन दिस. सो नाउ व्हाट डू यू थिंक? क्लोरीन हैज द हाईएस्ट एंट्रोपी एक्चुअली. अगर वो सेम टेम्परेचर पे होते हैं तो क्लोरीन की सबसे ज्यादा होती एंट्रोपी. एंड इफ यू लुक एट द पार्टिकल तो आपको तो लगेगा कि क्लोरीन की कम होनी चाहिए और फ्लोरीन की ज्यादा होनी चाहिए, क्योंकि क्लोरीन हैवी है तो उसको एनर्जी ज्यादा चाहिए मूव करने के लिए, है ना? लगता तो यही है ना.
Yeah.
बट इसके बारे में वो आपसे डिटेल में पूछता नहीं है. यू विल नीड टू लुक एट द बोल्ट्जमैन डिस्ट्रीब्यूशन ऑफ थिंग्स टू फिगर आउट के एनर्जी थोड़ी सी इसको ज़्यादा देते हैं अगर 1 डिग्री सेल्सियस का इसका टेम्परेचर बढ़ाते हैं, तो हाउ डज एंड व्हाई डज इट चेंजेस. सो इट्स काइंड ऑफ लाइक क्लोजली रिलेटेड टू हाउ द काइनेटिक एनर्जी ऑफ द पार्टिकल चेंजेस एंड ऑल दैट. एनीवेज, एंट्रोपी को कैलकुलेट करना आपको पूछ लेता है, वो बहुत ही सिंपल है. जस्ट लाइक बॉन्ड एनर्जी को कैलकुलेट करते हो वैसे आप एंट्रोपी को कैलकुलेट करते हो. फ्लोरीन क्लोरीन की एंट्रोपी ऐड कर देंगे CLF की एंट्रोपीज में से, उसको हम देख लेंगे कि जी शुरू वाली एंट्रोपी खत्म हो गई है, न्यू एंट्रोपीज हैव राइजन. So we can say the change in entropy is going to be the final minus initial or product minus reactant. So, for example, in this first example that I gave you, the standard entropies of these are 192, 131, uh, 193. So if I want to figure out how the entropy changes in this case, the standard entropy change, it's going to be 2 times 193 minus 3 times 131 plus, इसको bracket में कर लेते हैं, 192. You solve it, whatever the answer comes out to be. I'm guessing it will be negative because you have 4 moles on the left side, you have 2 moles on the right side. So it's going to decrease, obviously. So that's how you know the signs of entropy. बहुत simple सा concept है. It's not much. The second idea, as I said, is spontaneity. Spontaneity is when a reaction does not need external energy. कोई उसको external source नहीं चाहिए energy का. Sodium chloride, if you put it in water at standard conditions, it will dissolve right away because it's a spontaneous process. आप उसको stir करते हो तो वो थोड़ा तेज हो जाता है, but अगर आप ना भी करो तो वो dissolve हो जाएगा. But there are processes which are not spontaneous, and those are the ones that don't happen altogether. Foreign say, for example, you let some natural gas escape into the air. Wo foreign, it doesn't catch on fire. There's no flame that comes out. Why? Because the flame coming out and the combustion process is not spontaneous. उसको external energy चाहिए, external source चाहिए before it starts to react. So that is going to be non-spontaneous. ग्राफाइट, डायमंड जो है ना वो हमेशा ग्राफाइट में कन्वर्ट होता है. इट्स अ स्पॉन्टेनियस प्रोसेस. सो एवरी डायमंड हैज अ लेयर ऑफ ग्राफाइट इवेंचुअली, बट ऑफ कोर्स वो बहुत ज्यादा स्लो है, तो वी डोंट नोटिस इट इन द टाइम दैट वी हैव. एंड इफ यू कीप ऑन क्लीनिंग द डायमंड्स, ऑब्वियसली वो you will not notice it ever. Okay. So one confusion that students might have is that spontaneity is not how quick the reaction is. Spontaneity is just, does it happen by itself? That's the idea. कि उसको externally कहना नहीं पड़ता. सही? Now, that is important because spontaneity will lead us to something that's called Gibbs free energy. So let's look at this. किसी भी reaction में you have a system and you have surroundings. दोनों की entropy को अगर मैं add करता हूं तो I'm going to get the surroundings के उनमें कितनी entropy है and system की surroundings, the system की entropy. And I'm trying to understand कि एक reaction होया, उस reaction में surrounding का कितनी entropy change हुई है और system की कितनी change हुई है. Obviously, the energies that's going to be released or absorbed वो surrounding के लिहाज से होगी. अगर absorb हो रही है energy in an endothermic process, it's coming from the surrounding. अगर release हो रही है, it's going to the surroundings, right? So I can say that this surroundings में जो entropy की change आ रही है, वो कहाँ से आ रही है? वो reaction उसको disturb कर रहा है तो आ रही है. ठीक है? Otherwise तो कुछ भी नहीं हो रहा है, right? The reaction itself is going to release energy. Reaction itself is going to absorb energy, right? And that's happening from the surroundings. अब surroundings क्या होते हैं? Surrounding is the beaker in which you're mixing the solution. Surrounding is the person doing it. Surrounding is the air around it. The chemicals taking part in the reaction are the system. That's what makes the system. अब surrounding में energy आ रही होगी या उनसे energy जा रही होगी. जब energy surroundings को मिल रही है, so that is negative delta H. जिसका मतलब क्या है? कि when the surroundings are getting energy, it's coming from the reaction. And the way we describe it is, मैंने आपको बताया था कि the entropy is joules per Kelvin per mole. So delta H divided by temperature divided by moles will give you the entropy. But we take it to be 1 mole, so इस वजह से हम delta H over T कह देते हैं. Technically, this is the delta H over delta T. कि टेम्परेचर में कितना चेंज आ रहा है और डेल्टा एच में कितना फर्क आ रहा है. और इवन इफ फिक्स द टेम्परेचर तो वो टेम्परेचर की वैल्यू होगी उसमें. सो दिस इज द चेंज इन द एंट्रोपी ऑफ द सराउंडिंग्स. सराउंडिंग्स में कैसे एनर्जी एंट्रोपी चेंज हो रही है? बाय गेटिंग एनर्जी फ्रॉम द रिएक्शन. ओके, सिस्टम की एनर्जी एंट्रोपी चेंज क्या हो रही है? कुछ भी नहीं, सिस्टम की अपनी अपनी रहेगी. Why have I done it like this? Because now I don't have to differentiate between surrounding and system. I know that delta S is talking about the system, the change in entropy of the system, and delta H is causing the change in surroundings. Right? Are you following this? And when I subtract these two, I get a value, which is the change in total entropy, total change in entropy. Now, here's the thing, the total change in entropy has to be positive. And this change in entropy is what? This change in entropy is also some energy per unit temperature per unit mole, right? So if I change that, so that is also some energy. I'm going to call it delta G after Gilbert. I think uska naam pata nahi kaun sa Gibbs tha. Divided by temperature, and it's also negative delta G. उसकी भी reason बताऊंगा कि क्यों negative delta G. So this thing is negative delta G over temperature, just like delta S is negative delta H over temperature. So the negative part is just a mathematical abstraction. You will not be asked about it, ki negative kyun hai, positive kyun nahi, and all that. But one thing that you have to understand is that this has to be greater than 0 for the reaction to occur, because dunya mein entropy should always rise. Okay? Which means if I want this to be positive, I want delta G to be negative. Why? Because only a negative thing will multiply with a negative to give me a positive answer. So if I want a reaction to occur spontaneously, then delta G must be a negative value so that the negative applies with the negative and gives me a total change that is positive. And the total change has to be positive because entropy should always rise after every reaction. Otherwise, second law of thermodynamics doesn't work, which means that law is very inherent to nature. तो reaction नहीं होने देना उसने, nature ने उसको block कर देना. Okay? Now here's the thing. In the exam, they will usually give you values in kilojoules और किसी की values in joules होंगी. तो आपने make sure करना है कि उसकी values को आप convert करते हो. अगर delta S उसने joules पर something में दे दिया और delta H kilojoules पर something में दे दिया, तो you have to make sure that you change that. Okay? Similarly, why do we not mention moles here? Another reason is delta H is usually given in kilojoules per mole. So it's already included in the thing that you have. So now let me just convert it to a more pretty equation. I'll multiply the temperature with everything just to get rid of this T. So that gives me, this cancels out, and that multiplies with it. So minus delta G equals minus delta H plus T delta S. And just to take the negative away, I will bring this negative here. So delta G comes out to be positive delta H minus T delta S. And this is the kind of like the formula that we use for Gibbs free energy. This is basically telling that if Gibbs free energy is negative, then the change in entropy will be positive, which means the reaction can be allowed by nature. If delta G is negative, that means कि आपका reactions second law of thermodynamics को violate नहीं कर रहा, और जब वो violate नहीं कर रहा, वो होगा. Okay, so we can have different cases where this can be positive, that can be negative, और उसकी base पे हमने देखना है. So for example, if delta S is a negative value, then it will multiply with this and give you an overall positive value. So you have a value here which is positive and you have a value here which is positive. वो कब होगी? जब आपका ये वाला reaction endothermic है और ये delta S आपका negative है, कि ना सिर्फ वो endothermic है but endothermic के बाद वो solids बनाना शुरू कर दे gas से. So that's one example कि जहां पर ये भी negative हो गया and multiply with negative, positive हो गया, और ये भी positive हो गया. Positive plus positive gives you a positive delta G value. A positive delta G value means a negative change in overall entropy, not just of the system, but also of the surroundings. होने नहीं लगा वो nature में. Because that is going to be violating second law of thermodynamics.
Sir, could you please repeat this?
So I'm saying that I have a reaction in which it's an endothermic process. I have some gases which react endothermically and give me some solid. So the change in entropy in this process is gas se solid ban raha hai, so that's going to be negative. And if that is negative, it will multiply by a negative value. Give me an overall positive value. So ye wala portion of the equation is going to become positive. And if this is also positive, then the overall answer is going to be positive plus positive, positive. Del means delta G is positive. If delta G is positive, delta S will be negative because delta S क्या होता है? Negative delta G over T. And that's not going to happen. A negative Gibbs free energy is required for the reaction to be spontaneous, for the overall entropy to rise. Achha, let's try another way. Let's say this is negative and this is also negative. Now, in this case, this one whole thing is going to be positive. So, ye negative hoga, ye positive hoga. Then, if we want the reaction to be spontaneous, then we want कि जो positive value है ना, ये इस negative से छोटी हो. Because kind of like imagine it like this. ये आपके पास axis है, ये delta G है, ठीक है? अब जो T delta S है ना, वो उसको राइज करके ले गया, ऊपर ले गया, क्योंकि डेल्टा एस भी नेगेटिव था, टी भी नेगेटिव था और माइनस टी भी नेगेटिव था, तो दे मल्टीप्लाई, ब्रिंग इट अप हियर. नाउ इट इज अप टू द डेल्टा जी, डेल्टा एच सॉरी, टू ब्रिंग दिस वैल्यू डाउन, एंड इट हैज टू ब्रिंग इट डाउन और बिलो दिस एक्स एक्सिस, क्योंकि अगर वो इससे नीचे उसे नहीं लेके जाएगा तो रिएक्शन स्पॉन्टेनियस नहीं हो सकता, बिकॉज डेल्टा जी विल बी positive, and positive delta G means negative change in overall entropy. Now, remember, in all of this, temperature is always positive. Why? Because temperature is the thermodynamic scale. Kelvin में, it is just a measure of the movement of particles. तो movement कभी negative तो नहीं हो सकती, या movement होगी या नहीं होगी, zero ही हो सकती है ना extreme case में. So इस वजह से temperature has to be in Kelvin, positive. कभी भी वो negative नहीं हो सकता. So that means T is just a multiplicative factor. T is kind of like exploding the change in entropy that you have and bringing it in line with delta H. Acha. Now let's say you have an exothermic reaction in which delta S is positive. Kind of like solid से gas बन रही है, ठीक है? And solid burn कर रहा है और gas बना रहा है, या solid energy release कर रहा है और gas बना रहा है. In this case, the delta S is going to multiply with negative T, giving you an overall negative value. A negative value plus another negative value, overall answer is negative. So this is the case where definitely delta G is going to be negative. If delta G is negative, overall change in entropy is positive, which means reaction is spontaneous. Similarly, last case where you have...
Sir?
Yeah?
Okay, इसमें right hand side is positive. तो
Yeah.
doesn't it make के Gibbs will be positive और फिर उसका अगर minus के साथ multiply होगा तो वो minus हो जाएगा?
And what will that make the overall change in entropy? Negative, right?
Yeah, so like मतलब the reaction won't be possible फिर.
Won't be spontaneous.
ठीक है.
Possibility and spontaneity दो different चीजें हैं. Possibility तो बहुत सी और चीजों पे डिपेंड करती है कि उसको एक्टिवेशन एनर्जी मिल रही है कि नहीं मिल रही, ठीक है, उसकी कोलिजन्स हो रही हैं कि नहीं हो रही हैं.
Thank you.
सो यू जस्ट हैव टू अंडरस्टैंड दैट गिब्स फ्री एनर्जी के ऊपर वो क्वेश्चन पूछता है, और गिब्स फ्री एनर्जी का कॉन्सेप्ट सिंपली ये है, मतलब इसकी डिटेल में आपने बिल्कुल नहीं जाना, बिकॉज इसकी अनफॉर्चुनेटली इसकी डिटेल के लिए आपको थर्मोडायनामिक्स थोड़ी बहुत पढ़नी पड़ेगी, एटलीस्ट द फर्स्ट 3 लॉज ऑफ थर्मोडायनामिक्स. वो हमारे पास ना वक्त है और ए लेवल्स अलाउ भी नहीं करते हैं, रिक्वायर्ड ही नहीं. तो क्वेश्चन जो आपके पास आएंगे ना, दे विल ऑल सिंपली बी comparing this to the idea that for a reaction to be spontaneous, which means it can happen without external intervention, the delta G must be negative, so the overall change in entropy is positive. Now, a couple of questions related to this. What if delta G, what is the impact on delta G if you change a temperature? So for that, you have to understand what exactly is the role of temperature here. Let's say there is a Gibbs free energy which is hovering above the x-axis. मतलब वो यहाँ पे है, मुझे उसको 0 से नीचे लेके जाना है so that it becomes a negative and the reaction is spontaneous. So अगर किसी भी केस में, किसी भी रिएक्शन में the value of this thing, the overall answer is such कि ये पॉजिटिव है और ये वाला, ये पॉजिटिव है, ये इसको रिएक्शन को ऊपर लेके गया गिब्स फ्री एनर्जी को, मुझे उसको नीचे लेके आना है, और मुझे इतना नीचे लेके आना है कि वो इससे भी नीचे चले जाए और 0 से नीचे चले जाए. सो फॉर दैट यू हैव टू सी कि अच्छा कोई ऐसा केस हो सकता है कि हम एंट्रोपी इंक्रीज करा दें पॉजिटिवली. क्योंकि जब आप एंट्रोपी इंक्रीज करोगे, दिस पार्ट विल बी नेगेटिव. And if this part is negative, that means overall answer might be negative compared to this. So are you following it? It's kind of like saying you have x minus y. If y is negative, oh sorry, if y goes down, if the value of y is less positive, yeah, more negative, then overall answer is negative. So अगर ये positive हो जाता है, ये ऊपर चले जाता है, तो this has to go further down ताकि उसको जीरो पे लेके आए. तो अगर तो ऐसा कोई केस है, तो आप टेम्परेचर बढ़ा दो. जब आप टेम्परेचर बढ़ाओगे तो इन x माइनस वाई में y की वैल्यू इंक्रीज करेगी. जब y की वैल्यू इंक्रीज करेगी तो वो इसको नेगेटिव की तरफ लेके जाएगी. सो इन द केसेस वेयर एंट्रोपी इज पॉजिटिव, चेंज इन एंट्रोपी इज पॉजिटिव एंड डेल्टा एच इज ऑल्सो पॉजिटिव, तो फिर तो टेम्परेचर बढ़ाने से द रिएक्शन विल बिकम स्पॉन्टेनियस. सो इफ दे आर बोथ पॉजिटिव, endothermic reaction with a positive entropy change, that means you increase the temperature, reaction will happen more spontaneous. So many solubilities are like this. But in the cases where the temperature goes up, but the delta H is very high, or in cases where delta S is negative, in the cases where delta S is negative, then increasing the temperature makes the reaction less spontaneous. या क्यों? क्योंकि ये भी अगर नेगेटिव है और ये भी नेगेटिव है, तो ओवरऑल दिस इज गोइंग टू बी पॉजिटिव. तो वो तो अगर ये पॉजिटिव हो गया है और एक्सोथर्मिक रिएक्शन है, ये नेगेटिव हो गया है, तो यू नीड दिस वैल्यू टू बी बिग, बिकॉज इफ दिस ब्रिंग्स इट डाउन, तो ये वाला पोर्शन उसको ऊपर नहीं लेके जा सकता बहुत ज्यादा. बट अगर आप टेम्परेचर बढ़ाओगे, इट विल मेक इट लेस स्पॉन्टेनियस. सो इट ऑल कम्स डाउन टू x माइनस वाई. अगर आपका x नेगेटिव है और y पॉजिटिव बनता जा रहा है, y भी नेगेटिव है, तो यू वांट x टू बी हाई, मोर नेगेटिव. सो इट ऑल कम्स डाउन टू कि कौन सा उसको पॉजिटिव बना रहा है, कौन सा उसको नेगेटिव बना रहा है, और आपको टेम्परेचर उसमें हेल्प कर रहा है कि नहीं. सेकेंड क्वेश्चन इज व्हाट हैपेंस इफ डेल्टा जी इज जीरो. What happens then? अगर Gibbs free energy zero हो जाती है. Let's try to understand this. When Gibbs free energy is zero, this becomes delta H minus T delta S, which means delta S is delta H over T. दोनों equal हो गए. This implies the reaction has reached equilibrium. And then the reaction is just going to be there. ना concentration forward जा रही, ना concentration backward जा रही. Then you disturb the system. एंड व्हेन यू डिस्टर्ब द सिस्टम, तो वापस इसी प्रोसेस पे आने की कोशिश करता है, इक्विलिब्रियम को वापस एस्टैब्लिश करता है. सो वन सच केस वेयर डेल्टा जी इज जीरो, व्हेन अ लिक्विड बॉइल्स. सो व्हेन अ लिक्विड बॉइल्स, देयर इज वेपर प्रेशर that's obviously pushing downward, so there's vapor that is going back and becoming liquid. So condensation हो रही है उसकी, and there's liquid that's obviously vaporizing. So at equilibrium, when they have reached their boiling point, delta G is zero. So here's an example of this. Let's say मैं water को evaporate कर रहा हूँ, boil कर रहा हूँ, ठीक है? So what's the change in entropy of water? That is going to be delta H over T, ठीक है? And I'll get the values. Water की latent heat क्या होती है? Okay, this is 40 kilojoules per mole for water, okay, for vaporizing it. And the temperature at room temperature क्या होएगा? Sorry, वो boil करता है 100 पे, तो 373. Okay, so this is going to give me some value. So this is clearly telling me this is going to be positive, which means कि आपका overall entropy is going to rise. Of course, a liquid is evaporating, boiling, so it's going to rise. But the energy that you need to convert it to vapor, that energy is going to kind of like offset. Pay attention. The energy that you're supplying, the latent heat that you're supplying, it offsets the change in entropy. Now I'll take you back to grade 9. In grade 9, I told you one thing. मेरे से पढ़ी थी ना आपने grade 9. उसमें हमने कहा था कि जब आप किसी भी substance को heat करते हो, that heat goes or flows into two ways. Either it changes to the kinetic energy of the system, or it breaks the forces of attraction. When it changes the kinetic energy, temperature rises or temperature changes. And when it breaks the forces, state changes. Basically, वो जो kinetic energy थी, it was a matter of how fast or slow the particles are moving. If they're moving more, that means आपने heat दिया, वो move ज़्यादा करना शुरू हो गए, इसका मतलब है उसकी entropy rise करनी चाहिए. So उसका temperature rise करना चाहिए. But at the same time, the energy required to break the forces, वो भी जो उसकी एंट्रोपी में राइज होना है ना, उसको वो कैंसल आउट करती है, और उसकी वजह से उसका टेम्परेचर चेंज नहीं होता. And that is why when things are changing their state, temperature doesn't change, even though you're heating them up. So this whole picture that we used to show to grade 9 students, it's a simplified version of कि actually में हो क्या रहा है कि even though you're giving them energy and the particles are moving like faster and they should be having greater level of disorders, that is offset by the change in entropy is offset by जो उसकी entropy है वो, और उसके जो the entropy that's going to obviously increase, और जो उसमें kinetic energy में change आना है, the energy that is supplied, वो changes opposite होते हैं एक दूसरे से, and that is why the temperature doesn't change or temperature doesn't rise. Because अगर entropy rise करेगी तो चीजें will start to have more disorder, और वहां पे आप उसको जो एक्सटर्नल एनर्जी दे रहे हैं उससे वो उसका डिसऑर्डर अब ज्यादा बढ़ेगा, अदरवाइज गिब्स फ्री एनर्जी जीरो हो जाती है. डज दैट मेक सेंस? दैट एट इक्विलिब्रियम गिब्स फ्री एनर्जी विल बी जीरो एंड एनी चेंज इन स्टेट सिग्निफाइज दैट. तो आई थिंक 1 या 2 साल पहले इसके ऊपर क्वेश्चन भी आया था कि गिब्स फ्री एनर्जी जीरो होती है तो क्या होता है, बिकॉज इट्स अ वेरी इंटरेस्टिंग क्वेश्चन कि क्या सिचुएशन होती है वहां पे. So that is the main idea of Gibbs free energy, how its value affects the thermodynamic possibility of that thing happening, or the what you call the spontaneity of that process. And it is spontaneous if overall change in entropy is positive, and if all overall change in entropy is positive, that means delta G is negative, and delta G is negative. Based on this equation, we can judge it. Okay, so that is all for today.